Okay, we got about 15 minutes here till lunch. We're going to talk about a lot of the pieces that we did before break, and we're going to start with some pieces that we actually learned last year. Uh, when we're curve sketching, we want to put all the pieces together so we can sketch a really good curve. And we want to start by identifying the domain of functions. If you have a polynomial, the domain is all real numbers. But if you have a rational function, say something like 1 over x minus 3, what's the domain for 1 over x minus 3? What can x not be? The denominator cannot be 0. What number would give you 0 for the denominator? 3. So it would be x cannot equal 3. So, you know, that's just two very quick examples, but, you know, in general, you want to understand what the domain of a function is. Along with that, you want to be able to understand what the range is. We'll get to the range more in a second. But intercepts, when you find the x-intercept, you have certain x values, but the y value for x-intercepts is always equal to 0. And again, this is something we've talked about back in Algebra 1, Algebra 2, College Algebra. But just a kind of reminder that these are other points. We're trying to just collect as many pieces of data that we can to sketch a great curve. The y-intercept is going to be an x value of 0 and then a specific y value. A lot of times people forget how to do the x and y-intercepts, but that's just a piece. Symmetry. I think that the two most common pieces of symmetry that we've talked about that you can identify is if you have an even function, that means where all the exponents are even, then it's symmetrical about the y-axis. And if you have an odd function, say x to the third minus x, then it's, so all the exponents are odd, then it's symmetrical about the x-axis. No, symmetrical about the origin. Sorry. Took a stupid pill this morning. All right, origin. There we go. Stupid does not exist. Asymptotes. Well, asymptotes, in this situation, we would have a vertical asymptote of x is equal to 3, correct? We've learned that before. But often with asymptotes, we also want to look at end behavior. And this is where we're going to apply this idea. The limit as x goes to positive or negative infinity of the function. So when we look for asymptotes, we can A, look at where the function is undefined, but we can also look at the end behavior of the function. What happens as we go towards positive infinity? What happens as we go towards negative infinity? What does the function do? Does it flatten out towards a line? Does it look like a parabola? What does it do? And then we also apply our pieces of calculus that we know. And we want to look at intervals of increasing and decreasing, concavity, local mins and local maxes. We also want to identify points of inflection as well. So who can remember from before break, what do we do to determine intervals of increasing and decreasing? What do we look at? Close. F prime of x, the first derivative test. So f prime of x greater than 0 would be increasing. And f prime of x would be less than 0 for decreasing. So again, that's review, right? Everything we've written up here is stuff we've actually done before. We're putting it all together. It's a cumulative piece. Local max and local min. Well, a local max happens where f prime of x changes from positive to negative, and the minimum occurs where f prime of x changes from negative to positive. So local maxes and local mins are important to find as well. Concavity. What test do I use to determine concavity? Second derivative. It is concave up where the second derivative, f double prime of x, is greater than 0. And it's concave down where f double prime of x is less than 0. How do we determine inflection? Where it changes, concavity changes, and that's where it changes sign. So we have f double prime of x changes from positive to negative or from negative to positive. The range, it kind of just follows suit. You're not going to be asked to identify the range. It's just something you should keep in mind, and you'll you'll see as we do this. So a lot of times it's the local max or local mins help us to identify the range, but the other piece is the end behavior. So you're going to see this kind of take shape here. Okay, so it says use the guidelines up above to sketch the curve of x squared minus 2x, or x to the third minus 2x squared minus 3x. Now again, remember Newton back in the 1500s, as he's trying to sketch this graph, 1600s. How is he going to make sure it's very accurate? And so this is the process that he might go through. And so we're going to start by identifying the y-intercept. We identify the y-intercept by plugging in what? What does x equal for the y-intercept? I plug in 0 for x. And if you plug in 0 for x, what's your output? 0. So the y-intercept is 0. How do I find the x-intercept? I set the function equal to 0. I will factor out an x. So I have 0, 3, and -1. So those are my x-intercepts. Again, we're just trying to collect as many pieces of data that we can so that we can get as accurate of a graph as we can. Okay, as far as asymptotes, let's look at this function again. Is there anywhere where this function is undefined? No, it's defined for all real numbers. Its domain is all real numbers. So let's determine the end behavior. So instead of asymptotes, we're going to look at the end behavior. And we determine the end behavior by letting the limit go to infinity. Letting x go to infinity, identifying the limit. So I have x to the third minus 2x squared minus 3x. How do I evaluate that limit? What do you factor out? And you get x to the third times 1 minus 2 over x minus 3 over x squared. What happens here? This goes to 0, and this goes to 0. So you have 2 over a very large number, 3 over a very large number, it's going to be 0. Now, you plug in a positive number, and you cube it. What are you going to get? Yeah, so as the limit as x goes to infinity is infinity. So as you go towards positive infinity, the y values or the range will go towards positive infinity. But let's look at as x goes towards negative infinity. Instead of plugging in a positive, let's just plug in a negative. If you take a negative infinity and cube it, you would get a negative. So what this tells us is it's going to start down and it's going to finish up. Yep, you should look at where it goes positive and where it goes negative. All right, so that's kind of a stuff that we've learned before. Well, horizontal asymptote, I kind of wrote it there, but there is not a horizontal asymptote in this situation, nor is there a vertical one. But there is end behavior. In this example, we do have a horizontal and vertical asymptote. We'll do that when we get back from lunch. Okay. All right, so now I want to determine my other pieces, so I'm going to look at f prime of x. What is f prime? We're going to determine intervals of increasing, decreasing, local max, and local min. So I have to look at f prime of x. What is f prime? Does that factor? It does not. So let's use a quadratic formula on our calculator. What are our two spots where that's equal to 0? You get negative 0.54 and 1.87. No? Can somebody try it on their calculator and see if we get this? Okay, so Hannah will have to look at your calculator later on, okay? Oh, I thought I did too. Maybe you messed it up again. Maybe your brother's getting a hold of your calculator. F double prime of x. What's the second derivative? Where is 6x minus 4 equal to 0? 2/3 or 0.66, 0.67. Okay, let's do our test. This does not factor, so I'm just going to have to plug in a -1 into here and see what I get. -1 squared is 1, times 3 is 3. Plus 4 will be 7, minus 3 will be 4. So this is positive. Plug in 0 and you get negative. Plug in 2 and we get positive. For a second derivative, plug in 0, you get a negative. Plug in 1, you get a positive. This tells us some important pieces. Where is this function increasing? Good. And it's decreasing in between, so negative 0.54 to 1.87. Where is it concave up? 0.67 to infinity, and it's concave down from negative infinity to 0.67. True or false? I have a local max. Where it is the x value where it occurs? Negative 0.54. And we will finish up with these when we get back. We'll sketch the graph. And we'll do one more example. You guys will have an assignment. Okay. Here we go. We did the location of the local max. What's the location of the local min? 1.87. And what's the location of the inflection point? How do I get the y values? Plug them in the original. So I'm going to take my calculator. I'm going to go to the original function, which is x to the third minus 2x squared minus 3x. And as I type in negative 0.54, I get 0.88. 1.87, I get negative 6.07. And 0.67, I get negative 2.61. So what I want to do now is I want to create my very own sketch. I'm going to choose tick marks that's going to match to what I have. Looks like my x values go over to 3. So I'm going to choose x values of 4 of them. 1, 2, 3, 4. And since I go down to negative 6, I'm going to make tick marks all the way down negative 8. And again, you can choose how you want to represent this. This is just what I chose to do. So, so my x-intercepts and y-intercepts are 0, 3, negative 1. So I can have a local max of negative 0.54 and 0.88, 1.87, negative 6. I have an inflection at 0.67 and negative 2.6. So I just plotted these 3 points. And again, you want your graph to confirm the intervals of increasing, decreasing, concavity, its end behavior. again, as x goes towards negative infinity, y goes towards negative infinity. So you know it's going to start down. It also says that it starts by increasing. So you know you start down and you're going up. You know it's concave down right away. So there's a lot of pieces that you can put in here to confirm that your graph is correct. Then as you sketch that, I take my window and I guess my x min, I'll go -4, +4. Make a tick mark every one. My y values, we'll go -10. I kind of extend it a little bit further down there. +10, and then tick mark every 2. Hopefully, as I sketch my graph, it should look. I think that's pretty good. We've done that before. We're just putting it all together now with the intercepts as well as the end behavior. So, what do you think? That's kind of review, right? Whoop, wrong one. Okay, we flip over. We do the other one. Then we have your assignment. Example 2 goes a little bit more quickly. Okay, we look for the intercepts. To find the y-intercept, I plug in 0 for what? If x is 0, I get 0 over 2, which is 0. I want to find the x-intercept, so I set the function equal to 0. If it's, thank you, Katie, that was excellent. If you say it's equal to 0 or say 0 over 1, you would cross multiply. And notice that when you cross multiply, the denominator goes away, right? So think about this. If the numerator is equal to 0, then the entire function is equal to 0, correct? So where is the numerator equal to 0? Where is 3x equal to 0? Or x equals 0. So it looks like its intercept is right at the origin. Asymptotes. This is undefined for what x value? -2. So therefore, we have a vertical asymptote of x equals -2. -2 is not part of the domain. We will. The horizontal is truly the end behavior, okay? So as x goes towards positive infinity, as x goes towards negative infinity, that will give us some horizontal behavior. So A for the day, who can look at this and tell me as x goes towards positive infinity or negative infinity, what does the limit go to? Remember how we did that? Remember how we just looked at the largest term in the numerator and the largest term in the denominator? So I'll show it the long way. If you factor out an x, you get the x's cancel and this goes to 0 and you get 3, right? But I talked about just look at the largest term in the numerator, largest in the denominator, divide them, you get 3, right? So that means you have a horizontal asymptote of 3. That's the end behavior. It wants to look like 3. Okay, so we have our intercepts and we have our asymptotes. Now let's look at our first derivative and our second derivative. Our first derivative, what rule do you have to use to find this derivative? Quotient rule, derivative of the top. 3 times the bottom, x plus 2, minus 3x times what's the derivative of the bottom? 1. Over x plus 2, quantity squared. It's like I get a 3x minus the 3x, which is 0. What's the only thing you have on top then? 6 over x plus 2 quantity squared. Is the top ever equal to 0? No. Is the bottom ever equal to 0? For what value? -2. Yes, it is equal to 0 at -2. So therefore, we have to include -2 as a test point. We include where the derivative is equal to 0 and where it's undefined. That's where things that are interesting happen. Now, You can plug in values before -2 and after -2, but let's just think about it, folks. The denominator is always, the numerator is always positive over positive is. So it doesn't matter what you plug in, you should get positive over positive. If you don't, then you did something wrong. So it looks like these are positive. So our intervals of increasing are from -infinity to -2, union with -2 to infinity. I can't include -2. Why can I not include -2? It's an asymptote. It's not actually part of the domain. -2 isn't a value you can plug in. Okay, decreasing. It's not. It's never decreasing. The first derivative is never negative. I do the second derivative. In order to do the second derivative, let's do local max and local min while we're at it. Max occurs where it changes from positive to negative. Min occurs where it changes from negative to positive. F double prime of x. In order to take this derivative, what rule should I use? Thank you, Colton. Why do I use a chain rule? Move that thing to the top. What I love about this class is intellectually, I mean, there's not a lot of people that stick around for their senior year to take calc, right? So, I mean, you guys are pretty smart. But I love the terms that we use. Stick that thing on the top, then take the derivative. Yeah. All right. That's awesome. I love it. Way to go, Hannah. All right. So you did this because you wanted to do the chain rule. And the chain rule is easier than the quotient rule, isn't it? So what's the derivative of the inside? Inside. 1 through the outside, -12 times x minus 2 to the -3. So over x plus 2 to the third power. True or false? The second derivative is always negative. False. Why? The cubed will change between positive and negative. So therefore, this is not always positive. It's not always negative. So we have to just consider the one value, and that's -2, because that's where it's undefined. Okay? So now that we have that, let's test a point. We'll test -3. I will get a negative on the bottom and a negative on the top, which gives me positive. And then I plug in 0, and I get a negative on the top and a positive on the bottom, which gives me negative. Do I have an inflection point? No, I don't. Why? Because -2 is not part of the domain. It changes concavity at -2, but -2 is a vertical asymptote. It's not part of the domain. You would have to be able to plug in -2 to come up with the y value, and you can't plug in -2. But it does change concavity. And so we have it's concave up from -infinity to -2, and it's concave down from -2 to infinity. And so with this graph, it looks like, y equals 3 and x equals -2, that those are going to be important points to plot. I guess I'm going to go, I'll do 8s again. So we'll go 2, 4, 6, 8, 10. And x equals -2. Y equals 3. What is the only point that I can plot on this graph from my information? Well, the origin, thank you, it passes through 0, 0. And then you can use the information that you're given to determine which quadrants it's in. And I will use the fact that it's always increasing. So if it's always increasing, is it going to be in the bottom quadrant or the top here? It would have to be in the top. And then for the next part, it would be in the bottom. And you can see that that also matches with where it's concave up and concave down. You can tell it starts concave up, then it's concave down by our test. And if we, in fact, go to the graph on our function or on our calculator, 3x, and we divide by x plus 2, delete, delete, and my window, we'll just zoom standard. That should be pretty close, 10 by 10. You can see that we get a very accurate graph. Fair enough? Does this help summarize a little bit of what we learned before break? So what you need to do is you really have two assignments in front of you. You have a review that you need to be working on to get ready for the test. You also have this assignment, which I give to you right now. 4.5, page 270, numbers 2, 4, 8, 9, and 11. So you have 5 problems you're going to be doing a complete curve sketch for. What's that? I do not have that. No, I did not run copies this morning. I'm sorry.